When a beam or a frame is subjected to external loads, internal forces tend to develop. In the design of these structural members, for example beams, when the internal forces are not taken care of, it may result into catastrophic failure of the members themselves and therefore the structural failure. And this can even result into claim of several lives. Therefore, in the design of structural members such as beams and columns, these internal forces must be calculated and taken care of in the design. These include bending moments, shear forces, and also axial forces. And in this video, if you have not understood what the internal forces are, please, I have shared the link to one of the videos I've prepared that explain very well to you on internal forces and what they are. In this video, we are looking at a simple supported beam with a uniformly distributed load, and we will be required to first of all calculate the external forces, find the internal forces, which are, in this regard, we are going to look at the bending moment and shear forces, then be able to draw the bending moment and shear force diagrams. This is the simple supported beam that we are talking about, and we have the roller support here and the pin jointed support here, and we have a uniformly distributed load over a span of L. The uniformly distributed load is W kilonewton per meter. Now let us look at the free body diagram of this loading system. We have a pin jointed support here, and therefore it will result into creation of two reactions, that is one in the horizontal axis and another one in the vertical axis. Then at support B, since it is a roller support, it will only have a vertically upward reaction and of a magnitude By. Then for us to determine the total load, since it is uniformly distributed, the total load will be length, it will be length times width, whereby width is telling us the magnitude of the W in kilonewtons per meter. Therefore, it will be W times L, and this will give us the total load, which is WL, and since it is a uniform beam, then it will act at the center. That means it will be half L from support A and half L from support B. Now, for us to proceed and find external forces, we need to determine the forces in the X direction and forces in the Y direction. Then we take moments. So condition number one, summation of forces in the X direction must equal to 0, taking the forces in the positive X direction to be positive. Then we have force AX, and it is the only horizontal force, so it will equal to 0. Then we need to also determine the summation of forces in the Y direction, and taking the positive Y direction forces to be positive, then it means sum of vertically upward forces should equal to the sum of vertically downward forces. Since the vertically upward forces are only AY and BY, then the only downward force is WL. Therefore, AY plus BY will equal to WL. Now, sum of moments about point A should also equal to 0. We are looking at the condition, the equilibrium condition number 3. The sum of moments about a particular point must also equal to 0. And taking the clockwise moments to be positive, if we look at our loading, we have WL, which acts at the center, and it acts at a distance L out of 2 from point A. So its moments will be positive because it is a clockwise direction. Then it will be a clockwise moment, which gives us W times L out of 2. Then minus, because we have BY the other side at a distance L from A, So it will be minus by times L equals 2. Equals 0. Now, of course, we are required to find by, and the by is going to equal to WL out of 2. Now, since we have that value for by, we can also find for ay from equation 2. And since the equation is ay plus by equal to WL, then we can get ay as W minus by, and ay is equal to WL minus WL out of 2. Therefore, ay is equal to W out of WL out of 2. So we have determined the external forces, and therefore we are required to determine the internal forces, and therefore we are going to use the method of sectioning. We are going to make a cut at a particular section and expose it. So since we have a cut here, we can still give the free body diagram for segment 1 and segment 2 with the horizontal force AX, then the horizontal, the vertical force AY, WL out of 2. Then on the other side, we also have BY equal to WL out of 2. If we are taking this section to be at a distance x from point A or support A, then it means from the cut to the support B, it will be L minus x, since the whole length from A to B is L. Therefore, this side it will be L minus x. Now, if we take segment 1 and we draw its free body diagram, remember it has a uniformly distributed load. Since it is W, if it is over a span X, the total force will be W times X, and this will be Wx, which will act at the center. Since this is length X, then it will be X out of 2 from point A, and X out of 2 from O, where we made our section cut. Now we have to also apply equilibrium conditions. So sum of forces in the x direction must equal to 0. Ax, the only forces we have here is Ax and N. Therefore, Ax in the positive x direction, N is the negative x direction. So it will be Ax minus N equal to 0, and Ax is equal to N and is equal to 0 because Ax has already been determined as 0. Therefore, N is also equal to 0. Then we look at the summation of forces in the y direction. These forces should equal to 0. Then we know here, according to this free body diagram, the vertical forces that we are having are this force WL out of 2. Then we also have the vertical downward force Wx, and also the shear force that we have put. Because when we create a cut here, we are supposed to identify, or we are supposed to indicate the internal forces, which are the bending moments, the axial load or axial force, which is N, or the normal force N, and also the shear force. So the shear force is V. So if we indicate it vertically downwards, then this moment M is meant to counteract the effects of this shear force, and therefore it is going to act in the anti-clockwise direction. Now, if we sum the forces in the y direction, therefore we have WL out of 2, then minus Wx, since it is pointing vertically downwards, and minus the shear force V, since it is also pointing vertically downwards. So what happens is that we get our shear force as the Wx minus WL out of 2, and therefore this is going to be the equation that is going to give us the variation of shear force as you move away from point A to point B, since you, of course, you will be changing in distance x. Therefore, having determined that shear force expression, Then we need to also determine the bending moment. The bending moments, sum of bending moments must equal to 0, taking the clockwise moments to be positive. Then WL out of 2 is going to, we are taking moments about this point. So WL out of 2 is going to be a clockwise moment with a perpendicular distance x. So it will be WL out of 2x minus WX. WX acts at a distance x out of 2 from this point where we are taking our moments, and therefore it is going to also be in an anti-clockwise direction. Then minus m, which is the bending moment that we have under question, and therefore it is also going to act in an anti-clockwise direction. That's why we are subtracting it. Therefore m will equal to WLX out of 2 minus WX squared out of 2. This gives us the equation that describes the variation of bending moments as you move away from one support to the other, and this is going to be a parabola that opens up towards the negative y direction. So it means in this scenario we are going to have a maximum bending moment somewhere. So let us proceed. Now that is the equation that gives us the bending moment variation as you move away from one support to the other. Now the important points to note on the shear force diagram and bending moment diagram, we must know that when shear force is 0, then when it is equal to 0, we are going to see that we will have the maximum bending moment. So let us substitute the shear force being equal to 0. If we bring the expression for shear force, which is W out of 2 minus WX, if it is equal to 0, then we need to determine what value of x. At what value of x will that be? Will shear force be 0, and we will have a maximum bending moment at that point. So we know that W, since it is the uniformly distributed load, it will never be equal to 0, but L out of 2 minus x can equal to 0. So we find that the x value is going to be L out of 2, and this is the distance from A at which at which the shear force is going to be 0, and where the maximum bending moment is going to occur. Now, if we also consider segment 2, the same thing is going to happen. We are going, since we have created a cut here, then this bending moment should be equal to the other bending moment that we have calculated. The same thing should be with the shear force. Now on the other side, the shear force was facing down, and the bending moment was facing in an anti-clockwise direction, and therefore here it must face in a clockwise direction. We do this so that these forces cancel out each other, because if we are to have a balanced system, then this shear force and the other shear force the other side, they must add up to 0. This bending moment and the other one should also add up to 0. Now we know the length from this point on to the end of this beam to support B is L minus X. So if it is L minus X, it means the total load will be W into L minus X, and will act at a distance equal to L minus X out of 2 and L minus X out of 2. So if we sum also the upward forces, then they should be equal to 0, and then we will have V, which is the shear force, which is pointing upward. Then the also another external force at B, the reaction at B is pointing vertically upwards. Then of course we know this W into L minus X is pointing vertically downwards, and it will be negative. Therefore this shear force V is going to be WL L minus Wx minus WL out of 2, and this is going to give us the same expression of shear force as we have already determined. The same thing is going to be with the bending moment. When we calculate for the bending moment, we realize that we get the same expression, which is M equal to WLX out of 2 minus WX squared out of 2. Of course, this is as it was already determined. Now, maybe some information that we need to also discuss is that if we get the value for X where shear force is equal to 0, we can substitute it in the expression for bending moment so that we be able to determine the maximum bending moment. We get the value of bending moment where the shear force is equal to 0, and therefore if we substitute in the value of X equal to L out of 2, we substitute L out of 2 wherever X is, so it will be W times L out of 2 times L out of 2, then minus W out of 2 into X squared, so it will be L out of 2 squared, and finally the maximum bending moment is WL squared out of A. This value is the maximum bending moment and always expressed at the point where the shear force is equal to 0. Thank you so much. See you in the next video when we are looking at how to draw the bending moment diagram and the shear force diagram for this particular scenario. Thank you so much.